Hi everybody and welcome to the second tutorial of BIOB20. And today we're going to talk about binomial distribution and Mendelian genetics. So the way this course works, as you understand, at least the way we're going to try to deliver it, is that we're not going to spend some time on the previous episodes. We're just going to go forward. So every week there's a hard reset. Wherever we went, we just forget it, we move forward, and we go to the next topic. So it's not going to be the usual case where we're going to say, well, let's pick up where we left off last time, right? I hope this is clear. Every week, no matter how far we went in the previous episode, we'll be starting a new one. And so if you have missed some concept, if you found it hard to understand some of the things, well, it's okay. That's completely part of the plan because we're going to revisit them multiple times in different contexts. And I think it's going to be more efficient if we do it this way. We can have different applications, also different points of view, but more importantly, your knowledge is going to grow. And when you're going to revisit the concepts after having understood more things, it's going to be a little bit easier for you to connect the dots. And even more importantly, your knowledge of R is going to grow. So one of the main limitations at the moment is that most of you are not yet very familiar with R. It feels like a foreign language and you have to express some ideas in it. But at some point, it's going to be much easier to express yourself in R. And revisiting the concept now that you will have the good understanding of how R works, you'll see that the conceptual thinking will be much easier. So anyway, that's, like I said, that's the experimental part of the class, the fact that we're trying to teach statistics in a new way. So let's get started with today's activity, the binomial distribution / Mendelian genetics. Let's start with the problem already. In 1913, an undergraduate student named Alfred H. Sturtevant published one of the most influential scientific discoveries in genetics. This is absolutely amazing that this guy was an undergraduate when he published that totally landmark paper. Makes you feel really bad about yourself when you read things like this, right? But anyway, so lucky him. He was working on fruit flies in the laboratory of Thomas Hunt Morgan, who had just figured out the rules of inheritance for genes on the X chromosome. So people had understood that genes were on the X chromosome at that point, more or less, but the X chromosome was a little bit particular, and the credit goes to Thomas Morgan to figure out the laws of inheritance with the X, the sex, and the genes that are on the X chromosome. Back then, scientists knew that genes were on chromosomes, but they had no idea what they were made of. The fact that it is DNA would come only in 1944, and I give you the reference, the landmark work. Okay, so we're talking of a time which is approximately 20 years before people would even figure out that genes are made of DNA. So they knew that they were on chromosomes because they could see the chromosomes in microscopy, but they got it wrong. Nobody thought at the time that it could be DNA because the idea is it's too simple. DNA is way too simple to encode all the complexity of life. Can't be that. Must be something else. Yet Sturtevant found a way to map the genes relative to each other. So by the time we hit 1944, there were relatively complete maps of the Drosophila genome. Okay, people still had no idea what genes were, so think about it in terms of the conceptual thinking of people of those times. They had no idea of the biochemistry, and yet they knew that this gene is next to this one, approximately at that position around there on the chromosome. So it's all in their head at that point. And that's what is quite amazing about this piece of work, why I love it so much. It is astonishing that we knew the order of genes on the chromosomes way before we understood what they were. The development of statistics came substantially later, so Sturtevant did not perform tests or investigate the confidence levels of his estimations. We will use R to view his results in the light of modern statistics, of course. Okay, statistics were starting to be developed. Around 1910 was the beginning of the very first statistical test by a guy who called himself Student. The Student's t-test was the first invented test, but the bulk of statistics was developed substantially later, like in the 30s and even in the 40s, when really the concepts that we're trying to formalize now were put forward in a very formal way. So in the science of the 1900s to the 1930s, they're very sloppy with statistics. Okay? They just make measurements and they say it must be good enough. They didn't know because the theory came much later. The binomial distribution. So that's the part where you guys had to watch the video. So one comment about the videos and the quizzes. I was really impressed by the grades you got on the first tutorial. So several people got max grades plus the bonus points for being ahead of time. This is really impressive. So if you have a score which is above 2, that's already quite impressive. Okay? If it's below 1.6, of course, there's a problem because we had answered 16 questions. So in that case, it's like inattention or something like this. But if you're kind of already above 2, you know, 2 thumbs up for you. This is already very impressive. And some people got even the absolute max. So I'm quite happy with the things I've seen so far on the quizzes. The results are kind of high. And I think for the videos, it's the same. Like the grades are usually high. The questions are anyway not too difficult. And I've seen that people who come have mostly watched the videos. At least they've done the quiz, especially with the video. So that's what matters the most. Fruit flies found in the wild have a black body and red eyes. Sturtevant had access to mutants with a yellow body and with bright red vermilion eyes, they're called. That means just bright red. He knew that the mutated genes were on the X chromosome in both cases. We will denote the allele for a black body B0 and the allele for a yellow body B1. Likewise, we will denote the allele for red eyes R0 and the allele for vermilion eyes R1. In one of his experiments, Sturtevant crossed heterozygous females B0, B1. Okay, so if you haven't had any genetics before, it's kind of a fantastic opportunity to discover how that works a little bit. And I hope that the word heterozygous is not really putting you off that much. So I mean, just having 2 different versions of the same gene that you receive from mom and dad. So B0, B1 means that they have 2 different variants of the genes. And looked at the phenotype of the males in the progeny. Males have only 1 X chromosome, which they do not pass to their sons. They pass the Y chromosome instead. So in this case, the genotype of the father is irrelevant. We're going to come to that in a second. The alleles on the X chromosome in the male progeny always come from the mother. So the cross is here to remind you how that works. And if you have never seen this, it's not too challenging. So the female here has got 2 different alleles, B0, B1. The male has got something here on his X chromosome, but we don't care what that is in this particular cross. And facing the X chromosome, he has a Y chromosome. So the gametes meet, babies are born. And so if we count only the males, from their father, they received the Y chromosome, and from the mom, they received either B0 and B1. So the males can either be B0 nothing or B1 nothing. And so we can directly see their genotype on the phenotype, okay? Like if they have a black body, they have the black allele here, B0, and if they have a yellow body, they have the yellow allele. Super simple genetics in the case of males, because we can directly read what happens on their phenotype. And Sturtevant got 571 flies with a black body and 513 flies with a yellow body. Among the 1,084 males in the progeny of the crosses, 571 were black and 513 were yellow. From this, Sturtevant concluded that males were equally likely to receive the B0 or the B1 allele from their mother. Okay, so that's what I mean. Statistics were not developed. The way he writes it is like 571, 513. Ah, come on, it's the same. Don't bother me. Okay. Well, is it the same? No, of course not. 517, 571, and 513. These are different numbers. You cannot say they are the same. But are they now statistically different or not? That's a different question. To test whether this is indeed the case, we will need a new type of random variable. Last time we've seen that we can just shuffle things around. And this time we're going to go one step further and use the binomial distribution. So a binary event has exactly 2 possible outcomes that are labeled 0 or 1. The binomial distribution describes the total number of ones in a series of binary events that are independent and that have the same probability. Okay, so the idea of the binomial distribution is that you have a certain series of events, and either they're success or failure, or 0 or 1, or black or yellow. Okay, so there are 2 outcomes every time. You label one as 1, the other one as 0. That's a little bit what we had last time with either placebo or vaccine. Okay, so there are many cases that are covered by the binomial distribution. The binomial distribution is usually represented by the symbol B and P, where N is the number of events, sometimes referred to as the size, and P is their probability. We will not need the formula, but there it is. Okay, so that's the formula here for your own records. In case someone asks you, that's the way it looks, but I don't think that we'll need it a single time in this course. It's not needed. What we need is to be able to compute it. We don't need really to know exactly what that distribution is. For us, there's no particular advantage to it. So if you're interested in formulas, of course, learn it. but for that class, we won't need it. We are thus interested in generating samples from the distribution B1084 1/2. Okay, we had 1084 flies, and we believe, at least the assumption is that they're 50-50, either they get the black body or the yellow body, so that's why the probability here is 1/2. Because there are 1084 events in total, alleles B0 and B1 are assumed to have the same probability 1/2. Okay, that was the introduction. Now let's get started. Using the documentation if necessary, but use one random number from the distribution B1084 1/2 using the function or binom. I realize that I say or binom, but I say binomial, so I probably should say or binom, but I'm not going to change now, it's too late. So always going to say or binom. Note that the n in BNP is the parameter size of the or binom. Okay, so that's the whole point of that question, is that it's super confusing. The fact that there is a parameter called n, another one called size, another one called prob, and the way mathematicians write them down and the way R writes it down are extremely confusing. So that's a nest of mistakes here. But let's hope that it's going to work out fine. And as usual, for these random things, Quarkus use 1, 2, 3. Okay, anyone, any idea? What's the answer to that question? In the class, in the online, go ahead, shoot. And yes, go ahead. So sorry, say that again. Oops, or binom. 1, 1084, just like that. 1/2. Okay, so in principle that works. Okay, and what do you say? Yeah, exactly. We'll need the set seed as usual. So this works. Let's be clear. This works, and I don't like it too much because we can get confused about what is n, what is prob, what is size, etc. So this is why, in general, I prefer to name the arguments. Okay, so that we can be a little bit more clear about what we mean. Of course, here we don't believe that the probability can be 1084, but let's try to be a little bit more specific about the way the arguments are called. So what is this one here that's 1? Is it size or is it n? It's n, okay? In the function or binom, n is the number of elements you want in the output. You had one element in the output, so here that's the parameter n. What is the name of the parameter that's 1084? This one is size. Okay, so we had Ashley here giving exactly the same answer and same comment. I prefer in general when the arguments are named. Well, I'll just say something about this in a second. And here this is prob equals 1/2. We get a different number, of course, but that's because we didn't reset the random seed. So the full answer would be set seed 1, 2, 3. And here we got that. So the way parameters work with R is a little bit funny. So you're allowed to move them around. Okay, so here, let's see. Okay, I get something, so set seed. So I get the same thing here and there. You can see that I'm allowed to move the parameter prob around, and R understands perfectly well what that means. But imagine that we're doing it this way here. Well, this doesn't quite work anymore. Okay, so it works only if you name the parameters, and that's kind of obvious why. So you have two conventions. Either you name the parameter, and then you're allowed to put them wherever you want. But if you don't give them a name, then R is going to match them by their position. Okay, so it means that anyway, what I expect you're going to put first is this. What I expect what you put second is this, etc. That's all fine, and that's perfectly reasonable. Now the problem is that you're allowed to mix both. And so if you mix naming the parameters and the position, then the position starts to be really confusing what you mean by the argument in second position. Okay, so if you do something like this, okay, that can be quite confusing. Oops, it can be quite confusing what's happening here. Okay, because now it considers that this is the first position. All this to say, please stick with naming the parameters. That's the one that is the clearest, and that will avoid this kind of confusion that can be a little bit annoying sometimes. So R is considered to be a bad language by many people. One of them is that it allows you to do too many idiotic things with naming the parameters. Okay, you don't even have to name them in full. You can say per, because like saving a huge amount of typing by not writing the OB. And so the statisticians decided, yeah, that's good programming here. No, it's not. It's horrible defaults. But or lets you do that, lets you hurt yourself. But don't you worry, I won't let you hurt yourself. Please write the parameters entirely, okay? So the proper answer, doesn't matter how you get it, but for yourself, do yourself a favor and write this as the answer. Okay, fairly simple question, fairly long answer, but it's because it allowed us to go through these details of naming the parameters. Question 2, produce 1,000 random numbers from the same distribution using our binom and compute the average. Okay, so how do I do that? Which is the parameter that I change here? Size or n or prop? Yeah, n, okay, obviously. And I set it to 1,000. That's pretty difficult. If I press enter here, I'm going to get again full of zeros and ones. And it's not that I don't really want to do it, but there's also no reason to do that. So we can directly compute the mean here. Okay, the function mean is very simple to use. It's like the standard one. And so we get a mean of 541, but of course we need to use set seed. Set up and okay, so the proper answer is this one after the set seed here. Okay, that's the correct answer. Not particularly difficult question here. Once you know how our binom works, it's just a matter of using the interface. Okay, so we're set. We understand how our binom works, and finding the mean is just to have something to put in Quercus. Any questions so far, or everything is clear? Yes? So is there a way to round up or down? Yeah, of course, you have plenty ways to do this. I'm going to demonstrate some of them. Let's say that I'm putting this in the variable that I'm calling x. So you can try round x. What happens? Okay, so if you do just that, you get the integer value, the closest integer value. You also have two other functions that are quite interesting. There's ceiling, okay, so which is the integer value just above, and if there's ceiling, there's also floor, which is the integer value just below. Okay, so round, it will switch at 0.5. Okay, if you're closer to one, closer to the other. Ceiling will always default to below, floor, sorry. Ceiling will always default to the above, floor to below. And you can also say that if you want to round with one digit after the comma, after the point, then you can specify it this way. So if you want, I don't know, like 22 digits here, it doesn't add them, okay? But if you say I want 1 or 2, well, 1 was a good example, then it just keeps one of them like that. In general, don't do this for Quercus, okay? Because like I'm expecting that you're not messing up with the answers of R. But for yourself, yeah, of course. Like if you don't want all the extra digits, that's one way. So R uses the precision of computers, and this precision is not really up to R, it's up to the CPU. And so it just hides the digits from you. The maximum that it can do is 22. Oops. Okay, so when you set that and then you want X, now you get the full detail of what it means. So that's how it's represented in the computers. It doesn't allow you to have more digits because then you hit the limits of the computers. Like the CPU won't compute with more precision than that, but every operation you compute with R, it just shows the first 2-3 digits, but in reality, it's got a lot more in stack. And by default, I think options is digits is 7 or something like this. Okay, other questions? All right, so let's move on. Analysis with one gene. Now that we can easily produce samples from the target distribution, we can use a standard statistical analysis to test whether the alleles B0 and B1 are equally probable. So here I'm kind of, calling it the standard statistical analysis. It's just called a test. Okay, that's called a statistical test. That's what we've been doing so far. To this end, we need always 5 elements. Okay, that's the rule of 5 statistical tests, a null hypothesis, an alternative hypothesis, a protocol to collect the data, a test statistic, S, and a decision rule. And we're going to do this the same as last time, but a little bit more strict, a little bit more formal this time. And that's going to be the logic in general. We're going to try solving the problems first, and then trying to refine our solutions to make them more strict. I also realized that in the interactions I had with you this week, previous week, some people mentioned p-value, some people mentioned threshold at 95. So of course, some of you have been exposed to statistics before, and they're probably wondering, where is this all? We haven't seen any of that. What kind of weird statistics are you teaching us? We'll see it, don't you worry. The reason why I'm teaching it this way is that I first want you to understand what we're doing, and then we're going to give them names. I don't want you to learn a protocol by heart without understanding what's happening under the hood. So what are the null and the alternative hypotheses? Okay, let's start with the null. What's the null hypothesis here? Any idea? Yeah, in the back. Okay, exactly. So the null distribution, the null hypothesis is that the distribution is this one here, this binomial 1094 1/2, like B0 drawn from that distribution. And you said that the alternative is that it's not 1/2. Okay, so we have other options like the alleles are equally probable, they say in the chat. And so that is true, and that is not yet complete. Okay, what's missing here is that we're also assuming that the distribution is a binomial. Right? That seems kind of obvious, but we still have to assume that this is not at all the only option for events that are 0 and 1. And the key assumptions, there are two that we've seen about the binomial, is that we're assuming that the events are independent, and that's not guaranteed at all. Okay, like these guys, like these flies, are brothers and sisters. Are they really independent within a brotherhood or sisterhood? Well, they're brothers because we have only males. Okay, so is this really independent within family? We're not too sure actually about this. So we're still making the assumption that yes, this is the case. The other thing is that we say, whenever you do the experiments, whomever does the experiments, and whatever is the air temperature, whatever is all the conditions, this never changes. The probability of being either B0 or B1 doesn't change. That's a constant. And that's also a fairly involved hypothesis. So we're assuming much more than just the fact that the two alleles are equiprobable. Okay, we're also assuming the shape of the distribution. And that's quite important for the alternative hypothesis. The alternative hypothesis, and I insist, is not that the null hypothesis is false. It's not that, okay? So the null hypothesis says the distribution of B0 is this, B1084 1/2. The alternative hypothesis is not that the null hypothesis is false, okay? It's something else. And that's really, really important. So am I saying that the statisticians are considering that we're going to divide the world into two possibilities, H0 and H1, or like the null hypothesis and the alternative, and there are plenty of other possibilities that are neither the null nor the alternative? Yes, that's exactly what I'm saying. Okay, so that's, in a sense, that's an illogical approach. Like logically speaking, philosophically speaking, it is not satisfactory because we're not covering all the cases. Okay, so what are the null hypothesis and the alternative hypothesis? So if I said it's the null hypothesis, the alternative is not that the null is true, what is it? Well, that's what we said. Okay, is that the distribution is still binomial, but that here this 1/2 is not 1/2. That is what the alternative hypothesis is. So what about the case that the distribution is not binomial? We're not even considering it. We're not covering it. Okay, that's very important to understand this. We are not covering all the cases in a statistical test. We do not. Any questions? Yeah? but P is not equal to 1/2. Okay, P can be anything else, anything you like, just not 1/2. But it is binomial. Okay, so that is one key that people very often misunderstand about statistical tests, is that first, it's very centered around the null. Second, is the fact that when we reject the null, we accept a hypothesis, which is not the exclusion of the null. This is, again, a restricted hypothesis. And where we have to, there's no other way. Nobody has found a good solution so far. Maybe you have one, and I hope you do, where we could actually cover all the possible cases. We are covering only a portion of the possible cases. The protocol to collect the data was given by Sturtevant in reference 4. Here we will simply assume that he followed the principles of unbiased data collection, and we will not look further into this. Okay, that's extremely interesting from the point of view of genetics, from the point of view of good science. This is an amazingly high quality science when you read the paper, but we're not really in for that. We want to know a little bit more about the statistics here. So we're going to just move forward. So still, like this step number 3, in practice, when you have to do it outside the exams, this is really super important. This is where so many mistakes are made. Question 4, what statistic could be used to distinguish the null from the alternative hypothesis? There was a little bit of confusion about this. I saw this in the Q&A where I answered yesterday. So any idea here about what we could use to distinguish something that really is in favor of the null from being in favor of the alternative hypothesis? Go ahead. Yeah, the ratio of B0 to B1, basically. Yeah, okay, the ratio of B0 to B1. The number of male flies with B0 alleles, question mark. Any other ideas? Okay, so let's question the ratio idea. So like I said last time, the statistic is the key. And that's really what will make the difference between a good test and a bad test. Everything is about the statistic. The rest is kind of almost obligatory. Like the null hypothesis is always we always know what we want to test. The alternative hypothesis, even though that's not just the exclusion of the null, this is still within the realm of whatever we can understand, which is the binomial world here. But the statistic could be anything, and so we have to give it a good thought. So the ratio of, let's say, B0 to B1, let's think about it. What should be the ratio if the null hypothesis is true? What should be the value, more or less? 1, okay? So like both values are equally probable. That's one of the key ingredients of the null hypothesis. So when we take the ratio, we're going to divide two numbers that are equal. We're going to get 1. And another question now is, what is going to be the ratio if the null hypothesis is false? Sorry, I can't hear. Anything else, okay? So away from 1, so very high or very low. Very low, but positive, because we're taking positive numbers. Okay, so that's a good idea. We could use the ratio and say the target value is 1, very high above 1, we reject, and very low below 1, we reject as well. And we take only the values that are around 1, because that's kind of a 50-50. Okay, that's a very good idea for a statistic. Another one, the number of male flies with B0 allele. So we could do that. Okay, so what could be the expectation under the null hypothesis? Let's say for the sake of the discussion to not waste time, we have exactly 1,000 males. What should be in that case if the null hypothesis is true? The number of B0 males. Go ahead. 500. Okay, that's 554 if you want to be exact. But because we're too lazy to compute it by hand or by the computer, we said 500. And if the null hypothesis is false, what should be that number? Not 542, not 500. Okay, way above or way below. Okay, so these are two excellent ideas for null hypotheses. For statistics that we could use to test a null hypothesis. Why is that? Because they have a target value that really is associated with the null, and when they get away from that target value, then probably the null hypothesis is false, and we would rather accept the alternative hypothesis. Now, both ideas suffer from the same problem. which is that we have to worry about two ways in which they can be different from the targets. You see what I mean, right? It could be too high or too low. So we're going to find something that would like to solve this problem. It's not a very difficult problem, but still it's going to be annoying if we have to deal with it all the time. So we're going to find something that's solving that problem once and forever from the beginning. Okay, we're going to take the statistic, that is to say, take the expected value, that's 542, and we're going to compare just the difference to 542. Okay, and the difference in absolute terms, which means that if it's above 542, then we're going to count it positively. And if it's below 542, we're again going to count it positively. Okay, so we take the absolute difference. Now, same question. What is, if the null hypothesis is true, what is the expectation for the statistic this time? 0. Okay, so we've shifted things from being, I don't know, whatever, like 1 or 542 to 0. And that's usually why this is called the null hypothesis. We always try to find a way in which the statistic is equal to 0 if the null hypothesis is true. That makes it simpler. And if the null hypothesis is false, what is going to be the value of the statistic? Very high, very low? Any number? Not quite any number, almost any number. Like, yeah. And the point is that now it's always positive, okay? Because we're counting the distances always in a positive manner, then as long as we get a high number, it will count for both cases, when we're too high or too low. Okay, I'm going to try and draw this a little bit here, is that we had hypotheses that were kind of like this. We had the target value, which is there, and we say here, this is good, the exclamation mark, but we were thinking that on the left and on the right here, there were the rejection zones, okay? Over there. And it's fine, it's gonna work, not a problem at all. The issue is that we need to find two thresholds if we do that, the left one and the right one. That's not a huge problem, but it's still a problem. If we transform, and so here, for example, if we're taking the number of males, we could say that the target value was 542 here. Now, after the transformation, we have a situation where there is a wall here at 0. It's impossible for the statistic to be below 0. Okay, and so we're accepting the statistic, which is around 0, and we have a single rejection region here, but it counts for both cases. Is that clear? That by taking the absolute value, that's a simple trick that kind of symmetrizes the problem, and now we have just one threshold to find. So that's why we're going to take this one. We're going to take the absolute value of the difference to the expectation. All right? Questions? How is the the drawing thing here? Cool, huh? Sure. Okay, so the statistic is going to be the absolute value of the difference with 542, which is the expected value. To find a quantitative decision rule, we need to know more about the distribution of the statistic so that we can have clear expectations. Right. What we're doing here in this part is, can I change color? So, yeah, is that we're going to randomize under the null hypothesis. And of course, we're going to have plenty of points that are around 0, but occasionally, just because of, it's random, we're going to get points that are going to shift away from 0. That's because it's random. Rare events do happen. And they're rare, but they do happen. And the question that we're interested in is really, where do they stop leaking to the right? What is kind of a place where really randomly we're not very likely to see many of them? So it's okay if occasionally there's one that goes beyond the threshold, but the point is that it should be the case that we put the threshold at the place where almost all the points are on the left, and only extremely rarely the points would wander on the right. So that's what we did last time, basically. We're trying to find what are the expectations. These red points here are the randomized experiments. And based on that, then we can make a decision rule with a particular threshold. Produce a random sample of size 1 from the null distribution here using the function binomial, and compute the value of the statistic on this sample using the function abs for absolute value to take the absolute value. Okay, any idea, anyone? So first it says make a random sample of size 1. So this we've done before. So R binom n equals 1, size equals 1084, and prob equals 1/2. So that's the command here that we had before, and that's the one that generates the random samples. Now that's not the statistic, that's the random sample. We want to compute the statistic on this n equals 1 case. So what do you guys suggest? How do I do that? Yes? Yeah. Okay, so we remove the expected number here. Okay, so that now we have centered the distribution of the statistic on 0. Now the expected value is 0. And because we want to symmetrize it, then we put this within abs for absolute value. Okay? And so now I get numbers that are always positive, but you see that they're much smaller than before. Okay, like we get 4, 14, 3, etc., because they're actually quite close to the target. Yes? Yeah, that's a good question. Should we use the mean as the mean with like with digits, without digits? You should use the mean with the digits as it is like the normal mean. But here, okay, the 1084 is an even number. Okay, so it means that really the expectation is exactly 542. But when the case happens, in that case you keep the digits and you round. But OR does that for you automatically. And if you need to give an integer number, then use the rounding. But I can't remember if in Quarkus there are questions where rounding matters. I'll try to not make it an issue because nobody likes to first lose points on rounding conventions, and second on us having to regrade because of that. Okay. So in that case, it is exactly 542 because that's the expected value, because this is even. Right? So we got here an overview of the numbers that we get. You can see that they're much closer to 0. They're of course always positive. We're computing an absolute value, so of course they're positive. No problem with that. So these are examples now. We're not drawing from the sample anymore. We're drawing from the statistic. Okay, so these are examples of what the statistic will look like. And these numbers that I'm having here are exactly equivalent to the red points that I was drawing here. Okay, many of them are close to 0 here. Some of them will be high, but how high? Like, is, for example, the number 100 impossible with this distribution? Or is it still possible, after all, that you would have, a deviation of 100? So let's find out. So far, so good? Any questions? Okay, so let's move on. Produce now 1,000 random values of the statistic under the null distribution. Store them in a variable called null d. This stands for null distribution. Use the function mean to compute the approximate expected value of the statistic under the null hypothesis. So here we go. So how do I do this? What's the thing that I change here? N. Okay, we said here n equals 1. That's not what we want. We want 1,000. So what was the equivalent last week to produce a lot of random samples? Replicate. Okay, so this time we don't need replicate. The whole replicate call that we had last time is actually much more compact here, directly by using the binomial distribution. So we don't have to make it that complicated. So n equals 1,000. That's the same n as in replicate here. If I press enter, I'm going to get a sample from the statistic. It's going to flood the screen. I don't want that because it says what? Use the function mean to compute the approximate expected value of the statistic under the null hypothesis. So I need to wrap it up in the mean function. I forgot to do the set seed 1, 3 before. Okay, so let's do it. So here, before doing that, here I should have said set seed 1 to 3, of course. And then here the number is 13. Because it happens to be one of the typical numbers of the statistic. You got a deviation of 13 from 542, but that's not the only one. This is just because we have set the seed to 1, 2, 3. Now, set the seed again, and the mean of that thing here is 13.5. Okay? So that's the correct answers here. Any questions about this? Okay, does the logic start to sink in a little bit? Like we make a hypothesis, and then we try to predict what it says, because there is randomness in this hypothesis. These are not deterministic hypotheses like we're used to in math or something like this. Then we have a fuzzy hypothesis. And because we have this fuzziness due to randomness, we still need to choose a threshold. It has to be somewhere, and the place we choose it is based on the fuzziness of the predictions. So we need to know how fuzzy the predictions are. That's what we're doing now. Okay, so this average gives us an idea of the typical value of the score when the null hypothesis is true. But to make a decision rule, we need to know which values are atypical so that we can confidently reject the null hypothesis when the score is too large to be explained by chance. So what I mean here is that when we have all these red points that are there, okay, the typical value is whatever it said, around 13. Okay, fine, cool story. But we don't care about the value of 13 for the purpose of rejecting the null. This is a typical value for the null. What we want is an atypical. We want to know when too much is too much. You know, what is the threshold which is there, which is not really close to the average. We want it to be extreme. We're going to put the threshold at a place which is kind of unlikely to reach that value. Okay, if we want to reject the null. Does that make sense? We don't care about the average, about the typical. We care about the atypical. We want to see what becomes too atypical to be considered compatible with the null. So plot the histogram of the vector null d using the function hist. What is the range of values with highest frequency? So one way we can do this is just to inspect the null distribution. The null distribution is just the distribution of the statistic when the null hypothesis is true. So here we go. We need to, for example, store the results here of that thing in null d, what I forgot to do. Okay, so that will go into null d. Of course, before this, I must use the set seed trick. I can do it. Okay, and what we're asking is, oops, just to say, what is the histogram of null? An histogram is a fantastic graph. It looks like that, histogram of null d. So what is a histogram? What's represented on a histogram? On the x-axis, on the y-axis, what do we have? What makes a graph a histogram? Yes, go ahead. Right, so what really makes a histogram is that the y-axis is the frequency. Yeah, and on the x-axis? Right, so the x-axis, exactly, this is whatever you're studying. Could be anything. So the x-axis could be anything, well, as long as you care about it, but the y-axis has to be frequency or counts. Okay, this is really a representation of the frequency of each observation, each possible observation. Also, what makes it a histogram is that this is broken into categories, which in this case are relatively arbitrary. Okay, so they're separated into buckets of size 5. The first is 0 to 5, then 5 to 10, and so on. Okay, so here we've got a particular histogram, and the point of the histogram is that it informs us about the whole distribution of whatever you're plotting. So what are we plotting here? It says null D, but that's not null D. Yeah? Yeah, that's the absolute value of the expected and the observation, also known as the statistic. Okay, so what we have here is the overall representation of the statistic. That's the distribution of the statistic when the null hypothesis is false. True, sorry. When the null hypothesis is false, does that look like this or does that look different? Sorry, what? Yeah, so here we see the distribution of the null of the statistic when the null hypothesis is true. If the null hypothesis is false, does the distribution look like that or does it look different? It's a 50-50 chance. Of course it looks different. Come on, that's the whole point. Okay, like why do we even come here if they look the same? Right? So we want to distinguish, of course, the null hypothesis from the alternative. So what we hope is that when the null hypothesis is false, then this distribution will be different. And more specifically, we hope that it will be shifted to the right, that the values will be much more away from 0. We've said that 0, we keep it as the value that we're going to accept. And when the null is false, then we certainly hope that this distribution will be very much different. Yeah. So the question is, did I define the statistic this way so that we can turn it into a one-tailed test? Yes. It was to symmetrize the problem, really, is to go from a situation where I would have to have two thresholds, one on the left, one on the right, to having just one. Okay, so technically we are doing a two-tailed test at the moment for those who care about the detail, but we have a one threshold rejection region. Okay, and it is a two-tailed test because when the statistic is too big, we reject, but it could be too big because it's way above 542 or way below 542. Okay, that's why it's a two-tailed test. There are actually two regions where we reject it, but the trick of designing it this way, it's exactly what you said. It is only to symmetrize, to flip the two highs on themselves to get only one rejection region because it's going to be much simpler. And it will count for both of them. But technically, when we do that, the test is still a two-tailed test. Okay, so what makes a good test, a good statistical test versus a bad statistical test? I said it's the statistic. Okay, so what could we ask to a statistic to be really good? Going back to this histogram here, because we said the histogram looks like this when it's the null hypothesis is true, and it's not going to look like this if the null hypothesis is false. Well, what we want is these distributions to be as different to each other as possible. Okay, so that there is ideally no overlap. That'd be perfect, because then you just need one event to be able to tell for sure I know that the null is false or that the null is true. So that's what we demand in general with this test, is that we choose statistics, not just because they're different between the null and the alternative, but because they are maximally different in terms of their distributions. It will maximize the chance that when the null hypothesis is false, we're going to catch it. So let's answer the question. Plot the histogram of the vector null D using the function hist. What is the range of values with the highest frequency? So not here. The highest frequency is this one, that's the first bucket, and it goes from 0 to 5. Okay, it's a purely decreasing distribution. We're more likely to see small values than to see large values. We have never observed anything above 55. Okay, we don't know if it's 51 or 55 because we got these buckets, but we know that we observe plenty of values that are around 0 to 5. Most of them actually are small. So the answer is the bucket from 0 to 5. All right, time for a little break, but we're making good progress. We'll solve that problem, don't you guys worry. So let's meet that in 5 to 6 minutes at 6:09. We'll start again. So I'll stop the recording here. Pause the recording. So welcome back. Any things that you'd like me to go over again or to explain, or maybe some questions that you have right now? So before resuming, I forgot to do that. How can I forget that? A quick show of hands. Do we have international students here? Some. And in the chat, do we have international students around here? No, we don't have international students in the chat. Everybody's from here. Well, anyway, it was to thank the international students and to say that you're very welcome at the university. You guys are heroes. What you're doing is really difficult and the university needs you. So thank you so much for being here. And to the domestic, be good hosts, be nice to the international students, they're nice people. We need to show them that we're very nice people as well. That's all I wanted to say. So let's go back now to wherever we were. Okay, so we just have the histogram of the null distribution. And what we were saying is that this distribution here, we want it to be as different as possible from the distribution when the null hypothesis is false. Okay, but we don't know exactly the distribution when the null hypothesis is false. All we know so far is the distribution when it is true. And that corresponds to these little red dots that I have put here. If we did the histogram here of these red dots, what we would find is that the histogram should look something like that. Right? So pretty much what it looks like here on a real histogram. Okay, so that's the same representation, like having these red dots that are accumulating close to 0 and that are less and less frequent when you go to the right. It's the same as representing them with a histogram. Same information. All right. In order to design formal decision rules, we need to measure risks. Okay, that's the whole point here. We want to have a rational approach to risk-taking, to changing our mind, and to making decisions. One of the key concepts is the so-called level of a test, and that's what this chapter today is about. So the level of a statistical test is the risk of falsely rejecting the null hypothesis. In other words, it is the probability of rejecting the null hypothesis when it is true. The level is chosen by the analyst. Okay, that's a really important concept here, that of the level of a test. So what do we mean by that? So the numbers that we have, like the null distribution, shows us the value of the statistic, what it can be just by chance. Okay, and these distributions here, we sampled it to get all the, like a bunch of red points, like 1,000 of them. And as we know, it can sometimes go to the extremes. Okay, that's possible. It's rare, but that's possible. So when we see a point here which is very much on the extreme, are we sure that it's, so when are we sure that it's not coming from the null hypothesis? Okay, so if we have a point here which is there, can we be sure that this is impossible, that it comes from the distribution here in green? What do you guys think? Like, is there a point, a moment that is kind of an absolute, something that's objective way to say, okay, now this is really impossible. This cannot come from the green distribution. Possible, but low chance, I see. What do you guys think? Is there such a thing as a absolutely impossible point? Yeah. But the answer is not really. Okay. So if you think about it mathematically, the answer is no, but in practice, the answer is yes. Okay. The probability will keep decreasing until it's like extremely, extremely small, but it will never reach zero. So there's not a threshold which is mathematically defined as, okay, now that's impossible. But when we're talking of events that happen, once every 150 billion times the age of the universe, you could say that, yeah, no, it's just not going to happen. Stop it. So there are practical thresholds which are like, okay, that's practical. It's in practice impossible, but not mathematically. So that's the problem. We don't have a mathematical threshold for impossibility. We always have to accept a certain amount of risk. Of course, that risk can be so small that it's practically inexistent, but mathematically, there's always a risk. And that's what we need to think about. So we're going to put the threshold here somewhere. Okay, the one that I used, like the dotted line over there, is going to be somewhere, but no matter where we put it, there will always be a chance that out of sheer bad luck, the null, the statistic under the null distribution will be on the right side of this border here. So we have to choose wisely where we put this border. So, and knowing that no matter where we put it, then there will always be a chance that there's some point that are even more on the right. That will always be possible, at least mathematically. So where do we put the line? Well, we have to think. Always a good idea to think, actually. So the level of the statistic is the risk of falsely rejecting the null. What does it mean? It means that if we put the threshold here and we say whenever we observe a statistic which is on the right side of the threshold we reject, what I just told you is that it's always possible. It can always happen. And so the probability that this happens is the level. This is the probability that we make a mistake in the call, because we decide to reject the null when the point is on the right. The probability that we reject the null is the probability that the point is on the right. Okay, so there's always a risk, a positive risk. We cannot be 100% protected from it, and so we have to choose that risk. So what about we choose a small risk instead of choosing a big risk? That seems kind of the obvious thing. We say we're going to put this threshold here, just at a place where the risk is small. We cannot put it at a place where the risk is zero. That's just mathematically not possible. But we can put it at a place where the risk is not too big, acceptable. So what is acceptable? What do you guys think? 60. Any other idea what's acceptable? Yeah, 5%, 1%. So why do you think that 1% or 5% is acceptable? No particular reason. It's convention, okay? Because 1% is smallish, 5 because we have 5 fingers per hand, I suppose. But so there's no particular reason, why not 4.5 or 5.3? So these numbers that you will see in every statistical textbook, they come out of nowhere. Like there's really no particular reason why they're 5% or 1%. It's just that they're small, they're conventional, but you have to understand that there's nothing magical about 5%. And yet, what you will see in the community and in the textbooks is that people are fairly religious about this 5% cutoff. So why the religion? I don't know. I've never understood it, but people say less than 5%, that's we reject the null with confidence. More than 5%, we accept. That makes no particular sense, but it's so conventional that at that point, it's even hard to question whether this is a good choice. So be aware that mathematically, these numbers make no sense, but in terms of conventions, in terms of social and politics of science, you will not really be able to challenge them that much, these numbers. If you use a 1% threshold, that's fine. Everybody will like you. If you use another threshold, you're going to make enemies. So we don't want to make enemies. We take 1%, of course. But you have to realize that this 1% number that we're going to use is not magical. It's not that this is truly acceptable. Question for you guys. What should be a proper way to choose what is acceptable, if not convention? Any idea? Right. It depends on what we're studying, right? So uh, it depends on what we lose by being wrong as well. Okay, so in the end, of course, we lose pride always, and we want to have 95% chance of not losing pride. That's for sure. But very often, when you make decisions, you can quantify what you're losing and what you're gaining. If you're making a financial decision, you're going to win some money if you're right, and you're going to lose some money if you're wrong. Well, you can choose so that you can minimize your loss, for instance. Or if you're making a political decision, you kind of guess how much you're losing and how much you're gaining. If you're making a medical decision, you also know, okay, like what's the chance that the person will die because I made a mistake? What's the chance that they will live? Or what's the chance that they will have this horrible condition if I'm wrong and that I cure them if they're right? So you should make the decision not based on conventions when you go out there and you have real jobs that use statistics, but based on a real analysis of the cost and benefits. That's kind of obvious, right? That it should not be 5%. So it's completely okay from the point of view of statistics and also of science to say, I'm not going to use 5%, I'm just going to say, for the sake of the problem or the person that I'm trying to treat or whatever I'm interested in, then I'm putting the threshold here because I measured the cost, and being wrong this way will cost me much more because the person will die, for instance, and being wrong the other way where they will just have an itch. Okay, so it depends, and there's absolutely no way to answer all this in generality. So why is this 1% conventional and 5% conventional if it always depends? And that's because of the history. Before we had computers, people had to, it was really, really tedious to do these jobs. So they made so-called statistical tables, which is something that you will probably never see in your life. But that's the way I learned statistics. We had tables. We had to go to page 33, look up the table, and the tables, you can make complete books of tables, but at some point they got bored. So we say, we're going to make it for only 3 values, 5%, 1%, and 0.1%, and that's it. And so that comes from the time when everybody had to use these tables and there were 3 values. So you had to pick one of those. And people didn't die. They're still around, and they're still saying that, well, it was nice before, so we're still using them. But there's nothing magical about them. All right, I got sidetracked, sorry about this. So the level is a risk that the analyst is willing to take. So the value is typically small, like 1% or so. If the level is chosen by the analyst, then why not choose 0%? First, because we can't. Okay, there's always a mathematical risk that the impossible or what looks impossible will happen. We could choose a 0% risk in terms of practicalities, something that will really never happen in the world where we live. But even that is not a good idea. Even if you could, it's not a good idea. We will see later when we discuss the notion of power of a statistical test that there is a cost to lowering the level. For now, we just set it to 1% and we think it's cool, but we maybe hurt ourselves by putting it too low. We'll defer that discussion for later. Without going into technical considerations, we will set the level to 1% for the present analysis. So question 8, what is the cutoff value x such that there is only 1% chance that the statistic is greater than or equal to x when the null hypothesis is true? So what I'm asking is, where should we put the line here such that 1% of the points are on the right side and 99% of the points are on the left side? Where is that line? Any idea, anyone? Maybe not where is that line, but how do I find that line? Yes, go ahead. Okay, so my best friend is going to be the quantile function. Why is that going to help me here? And why do I put in quantile? So what is the quantile? How do I find a quantile distribution? Now D 0.99, says Marco. So I suppose Marco means that I do that. I suppose that I do that. And here we go. That's what Marco is suggesting. So what does that do, this command that's here? Quantile null D 0.99. And I think you had to think about this with the videos. What does that do? And why does that work? And what's the equivalent process of this computation here? Yeah, right. Okay, the first equivalent process is to compute the area here in the histogram and finding the point where the amount of surface, which is on the right side, is 1%. Okay, that's the first equivalent calculation. So it's the place where you have 1% of the mass, 1% of the total probability on the right side. Okay, the other equivalent process, for those of you who are not very comfortable with this quantile function, what the quantile is actually a sort. Okay, so here I'm going to flood the screen, sorry about this. But if we sort the values here, okay, we can see that this looks like that. So we've got a bunch of zeros and then a bunch of ones. So all the numbers, of course, are like single-digit integers, etc. And at some point, we see that we're going to start skipping values like 48, 50, 51, 55. So like this becomes kind of more and more sparse here. So we put all the numbers on a line, and we say that we can, once they're sorted, and we got exactly 1,000 of them. Okay, if we take the one that is at 9,990, okay, which is 85, 6, 7, 8, 9, 10, is this one. All right, so here I have 99% of the values that are on the left of the 42 that I highlighted here, and 1% of the values on the right. That is what a quantile is. So the median, which is the quantile at 0.5, means sort the values, pick the one in the middle. Okay. And so by definition of the median, you have half of the values that are below, half of the values that are above. And by definition of the quantile here at position 0.99, you have 99% of the values that are below and 1% that are above. So that's strictly equivalent to sorting them manually like I did, and then picking off the value that separates the 1% from the 99%. So quantiles are really, really super easy as long as you think about them in terms of sorted values. And the point is that doing this process, it's fairly manual. Okay, I need to count the values, etc. And you see that I use the fact that this 40 here is 985, and then I had to count manually to find that this is the value I'm looking for. It's not a very automatic way of finding the answer. Quantile, on the other hand, is automatic and instantaneous. And the point is that here, to find the quantile, the manual way, need to sort the values, but quantile does not need to sort the values. I mean, it does, but it doesn't show it to you. So it can do it on literally any scrambled data. Okay, it doesn't depend because it will always resort them internally for you. So just to make it clear, here I'm computing the nullity this way, but if I scramble, oops, definitely scramble. Sample nullity will just change the order. It doesn't change the value at all. Okay, so no, like quantile works on any data set, sorted or not. So that's what the quantile function does. And that's indeed the value that we can use. 42 would be a good point because there's only a 1% chance that if the null hypothesis is true, that you'd observe a statistic that is bigger than 42. Okay, all this for that is to say that here, if we choose that here at 42, okay, then there is a 1% chance that the statistic is on the right side of the 42, and there is a 99% chance that it is on the left side. So that here, 42 is the threshold, it's the key. But we had first to decide that we're going to work with a 1% risk. All right, so far so good? That's a very important comment that we made here. Okay, that the way that you find these thresholds is that you first choose the risk, and then use the quantile function to find where is the threshold that corresponds to the risk that you're willing to take. Okay, so what is the cutoff value? That's 42, such that add a red vertical line at this value in the plot of the histogram. So what's the function to do this? Do you guys remember? Yeah, AB line. Okay, and then we say V equals 42. And I want it red, so I'm going to use call equals 2, which stands for red. So on my graph here, I have seen that the threshold is here. As you can appreciate, it's really hard visually to know that this little area here is 1% of the big area. There's no way that, I cannot, maybe you guys can appreciate ratios of surfaces like this, but I would really not be able to tell that this is 1% here. I realize that this is much smaller than the big, but I really cannot say that this is 5% or 1% or 0.1%. So better use the function quantile than to try to use your eye here. But that's it. That's the different ways of thinking about this process. Sort the value, cut so that you have 1% on the right, or use the function quantile, or use the histogram and have 1% of the mass, 1% of the surface on the right of the threshold. Having chosen a level, we now have a threshold, of course, for the decision rule, and we can decide whether we believe the null hypothesis or not. Question 9, finish the statistical analysis and conclude about the null hypothesis. So, what do we conclude? How do we conclude, actually? That's the final step of the statistical test. So we have explored all the ways that the statistic can behave, but we have not looked at this, the way it did behave. Right? So we have to compute the statistic in the data. So what is the statistic in the data? Let's go back. So we had 571 black body flies. So here we go. That's 571 minus, what is it again? 542, right? So 29. That's the value of the observed statistic. So 29 is here. Okay, like around here. So what do you guys say about the null hypothesis? Do you accept it? We reject it? We accept it. Okay, why do we accept it? Yeah, that's what we decided. So we got to stick to what we decided. So less than 42, exactly. We said 42 is the cutoff. 42, above 42 we reject, below 42 we accept. So what is below we accept. So we say that indeed the Sturtevant was right. There is a 50-50 ratio between B0 and B1. Okay, we have no evidence that this is not the case. So why are the numbers not exactly the same here? Well, just the way it is. Like you have 1,000 flies, you can't expect to have them exactly identical. There is some randomness, but this randomness is completely within the bound of what we can expect. So that's all good. Let's move on. Sturtevant then focused on the color of the eyes in the same cross. The females were heterozygous, or 0 or 1, and once again the genotype of the fathers was irrelevant, because he considered only the males in the progeny. Sturtevant obtained 574 males with red eyes and 510 males with vermilion eyes. So the cross is here. It's more of the same. The numbers are slightly different though. Question 10, perform a similar statistical analysis to decide whether the alleles R0 and R1 are equally probable. Darn, spend an hour and a half to get there. We have to do it all over again. We're never going to finish. No, don't worry. We're becoming good at that. So statistical test reflects 5 things. So what is the null hypothesis? Same as before, exactly the same. Okay, like the problem is exactly the same in reality. The only difference with that problem is that the numbers that we observe are slightly different, but they're even the same flies. Okay, so null hypothesis, the same as before, is that the distribution is this one. Alternative hypothesis, what is it? Same as before. Nothing has changed. Okay, it's the same problem. protocol. It's even the same protocol, of course. The test statistic, we're not going to change it. And the decision rule, we're not going to change it either. So this one is actually trivially simple now. We just have to compute the statistic, the observed statistic in that case. We have done all the work already. Does that make sense for you, that the problems are exactly the same in terms of what we believe, what we assume, and what we want to go through is exactly the same. It's just that we've done it twice, one with the body, the other one with the eye. So let's wrap it up then, if this is all finished. So we just need to compute the value of the statistic, in that case, 574 minus 542, 32. What do we conclude? Yeah, same thing. Okay, we're still below 42, so same decision rule. Well, same decision. Okay, does that make sense for you, that we can fast forward extremely, to the extreme here because we've done all the work before? It seems yes. Analysis with two genes now. Sturtevant actually recorded both characters simultaneously for every male, not just one at a time. Out of the 1,084 males in the progeny of the cross above, 385 were black with red eyes, B0, B or 0, B0 or 0. 186 were black with vermilion eyes. 189 were yellow with red eyes. 224 were yellow with vermilion eyes. So here's the cross. Okay, it's slightly more complicated in the sense that they still get their alleles from the mothers, but when you have B0 and O1, obviously they have switched chromosomes. Like the B0 or 0 were on the same chromosome, and then B0 got together with O1. So that's called the crossing over, for those of you who know genetics. And that's actually one of the ways they were discovered, is with this model in Drosophila. But back then it was just the beginning. Sturtevant was still very much puzzled about this phenomenon, and he had the idea of pushing it to the limits. Sturtevant knew that in the 1865 landmark work of Gregor Mendel, it was shown that characters are inherited independently. An English translation is available in reference to, for those who are interested. It's actually a very interesting piece of work. It's hard to read a little bit. But Gregor Mendel did not know that genes are on chromosomes. This did not exist at the time of Mendel. And Sturtevant was interested in testing whether characters were inherited independently, even when they were on the same chromosome. Okay, so was Mendel wrong? Maybe. And the answer is, of course, he was wrong. We just could not know that genes were on chromosomes. So independence in statistics, two events are independent if the probability that they both occur is the product of the probabilities that each one occurs individually. Mathematically, A and B are two independent events. If and only if the probability of A intersection B is the product of their probabilities. Okay, the probability that they both happen at the same time is just the product of each of them. That's what defines independence. Since the frequency of the allele B0 is 1/2, that's what we concluded so far, and that of the allele R0 is also 1/2, also just concluded it, the frequency of the genotype B0 or 0 should be 1/4 based on our hypothesis. Okay, if the alleles are inherited independently. In other words, the number of genotypes B0 or 0 should be distributed as a binomial with probability 1/4 this time, not 1/2. Question 11. In this context, what are the null and the alternative hypotheses? What statistics should we use to discriminate the null from the alternative hypothesis? I'm listening. What's the null here? Go ahead. Yeah, so that's the null hypothesis, that the B0 or 0 occur 1/4 of the time. And we complete it by saying that with a binomial distribution. Here we're pushing it. We're saying more things than just 1/4 at a time. We're also saying that this is a binomial distribution. That's the null. What's the alternative? Go ahead. Anything but 1/4, but still a binomial. Okay, we still believe that this is a binomial distribution. We're only considering the case that things are binomial. Okay, so null hypothesis and the alternative are not the same as before, but almost. We just have changed the target. It used to be 1/2 minus 1/4. What statistic should we use now? Any idea? Yeah, almost the same as before, but instead of doing that, we're going to take this 271 as the expected value. Okay, so we're taking the absolute value with the expected, same as before, but now the expected has changed. It's 271 now. Okay, good with everybody? Like it's more of the same, it's just that we're revisiting different ways of solving that problem. Produce 1,000 random values of the statistic under the null distribution, store them in a variable called null d, use the function mean to compute the approximate expected value. So it's the same as we did before, but this time the details are slightly different. Okay, so here we go again. We say that our binomial is the way to sample from the binomial distribution. We want 1,000 of them. Okay, the size still the same, it's 1,000 as before. And now the novelty is that the probability is 1/4. And the question asks us to put this into what we're going to call null d. And I will need to put the set seed trick as usual. Okay, so set seed 1, 2, 3. And now if you've done this, you have exactly the same null distribution as I do. And we can compute the mean, null d, null distribution of the, I did it wrong, sorry about that. So here, what I'm sampling is the sample, not the statistic. Okay, so I get numbers that are like in that range. I must not forget to remove 271 and take the absolute value. That here is the statistic. You can see that the numbers are all positive and much smaller, closer to 0. So that's why we want to sample, not just the number of males, but the statistic. That's what we're interested in. And that here is the null distribution, or a sample from the null distribution to be more accurate. And what's missing is the set seed trick. So again, it's what we've seen before. The only thing that changed is the 1/4 here and the 271 that is here. Okay, so the 1/4 is because now this is the new null hypothesis, and the 271 is because it's the new expected value, so we need to adjust the statistic to match the new null hypothesis. And based on that, when I compute the mean of the null distribution, I get something that is smaller. Okay, it's 11.512. Okay, it's not half of the previous mean. It's not this at all. So the logic is a nonlinear logic here. Anyway, so that's the answer. It's 11.512. And so we're done. What is the cutoff value x such that there is only a 1% chance that the statistic is greater than or equal to x? Same question as before. Right? So like it's even copy pasted. Add a red vertical line at this value in the plot of the histogram. So how do we decide that? I can make a new histogram of the null distribution. It looks like this. It's very similar to the previous one. You can see that the values here are not exactly the same. It used to be 55, so it's slightly more protracted. And yeah, indeed, the values are a bit smaller than before. Not much more smaller than before. So that's the histogram here. How do I find the threshold working at 1%? Go ahead. Exactly, no change. Okay, so this part is that the quantile null is 0.99. It's 36 this time. Okay, it's a little bit below. It used to be 42 with the previous null hypothesis, and now it's 36. And so using the function AB line, V equals 36, so for vertical. So it's there. So that part here is 1% of the area which is there. Okay, so this is becoming kind of a little bit automatic. That's becoming more natural to do this operation when the problems are so similar. So our new threshold is 36. Finish the statistical analysis and conclude about the null hypothesis. So what's the final step after we've done the 5 steps? How do we finish? Right? And it's 385 minus, so we count 385 minus 271, and we got 114. The opposite, okay? So that's above the threshold. It's like way, way above the threshold, even, or not even close. So in that particular case, when we go back to the to this graph here, it would be like super, super far, not even on the graph, okay, like way, way to the right. So what do we conclude about the null hypothesis? Reject. Okay, then we reject. There is no chance that a value of 114 would be observed just by chance. The largest we obtain is somewhere around 50 out of 1,000 samples. And even if we had more, we'd never obtain such a value. So it's becoming too unrealistic to be compatible with the null. So we're cognizant of the fact that there is some fluctuations, fine, but too much is too much. 114 is way, way above the threshold. There's much less than 1% chance that this would happen just out of bad luck. Okay, so instead we change our hypothesis. We say it's much more likely that something else happens, and therefore that the probability that we're looking for here is not equal to 1/2. Okay, so we reject the null. We do accept the alternative, which means we still believe that the distribution is binomial, but not with probability 1/2. So first, good. So we've seen examples of both rejection, acceptance. Reject the null hypothesis, says Marco. Absolutely. All good? All right, so estimating the linkage. Sturtevant went further than observing that genes were not inherited independently. He also used the probability of association between the alleles as a distance between the corresponding genes. And that's the genius of Sturtevant. Like he just realized that depending how frequently, how often we can see these associations between B0 and R0, okay, because they're not independent, then how often they're together will tell us how close they are on the chromosome. So we can use that. We don't know whether it corresponds to real physical distances because they didn't know what genes were, but we know that they correspond to at least ideal distances. And so he came up with a unit that he called the centimorgan because he was working in the lab of Thomas Morgan. And so as a tribute to his beloved teacher, he called the unit the name of the teacher. In his footsteps, we set out to estimate the probability of occurrence of the genotype B0 or 0. For this, we can use the maximum likelihood method, whereby we screen hypotheses and pick the one where the observed events are the most probable. Okay, that's something that's really new. That's a very new way to think about gaining information for us. And we're going to introduce that concept now in this chapter. But the next chapter will be all about maximum likelihood hypothesis test estimation. Okay. Produce 1,000 random values from the distribution binomial 1084 1/4. How many times does the value 385 appear in the output? So that here, we kind of just did it. That is the null distribution. Okay, you can do it again if you want, but we had this. It's not the null distribution now, not completely accurate. Sorry about this. So what we have computed here is the statistic, but we're not interested in the statistic. In that case, we want to compute really the sample. So we're removing the 271 and the absolute value here. Okay, so we're going to put this, we're not going to call it the null distribution. We're going to call it the D for distribution, out of imagination. So here we go. I've just sampled here from the binomial distribution of 1084 and probability 1/4. And I need to here get the set seed trick. So how do I count? Well, let's see the D here, right there. How do I count how many of these values are equal to 385? 385, sorry. Anyone remembers? Go ahead. Double equal sign, exactly. Okay, so we could just look at it like this and try to see if we find it. And obviously the numbers are a bit too low so that we can find maybe even 285, or in the range of 250, 60, but not even 300. So here we can see sum D double equals 285. That's what works. 0. Okay, so I'm going to spend a second explaining that trick a little bit, if it's still mysterious for some of you. Let's see what happens internally when I just do D equals 385. I get something like that. Okay, it's just false, 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 false. You see that what it does is that it compares each and every value individually with the target, and it's returning true when it's equal to the target, and false when it's not equal to the target. So that's what's inside the sum, and the sum will count true as 1 and false as 0. That's why it counts the number of times that this test is equal to true, which means how often D is equal to 385. So never. So that tells us that 385 is what we have observed. It's really the value we have observed, not the statistic. The probability of obtaining it by chance when the null hypothesis is true is very small because I haven't seen it a single time out of 1,000 trials. Okay, so that tells me that this value here is incompatible with the null hypothesis, but this we had already figured out. We had already rejected the null. So it's just a matter to check that, yes, indeed, this value is kind of not compatible with the null. But that's reassuring. We have already rejected the null. Does that make sense for you? That we did not expect, after rejecting the null, that this value would be all over the sample that we generate. It's too high. Question 16, repeat the procedure of question 15 by setting prob to 0.30, 0.35, 0.40, 0.45, which is the value of prob, such that 385 appears most frequently in the output. So what we're doing now is kind of a funny idea. We're going to change the parameter of the binomial distribution until we obtain 385. So let's do it just to see what happens, and then we'll comment on it on whether it makes sense. So what does the question say? We don't need this anymore. Repeat the procedure, but change the value of prob. So the procedure is actually to do this here. Instead of calling it D, is to say sum. This is equal to 385 and 0. Sure enough, that's 0. So here we go. We say not 1/4, but we start with 0.3. Okay. So when the probability is equal to 0.3, we don't observe it at all. But we're asked to try different values here. When it's 0.35, then we do observe it 28 times. 40. No, not anymore. And 45. No, the train has passed. Okay, it was only at that particular value of probability of 0.35 that we did observe that event. Okay, so now you can do it with the set seed. 1, 2, 3, but nothing's going to change. Okay, in the sense that the only case we're going to see them is here. You're going to see 21 of them, but just before and just after, these are, if I remember, not comparative. 0 and 0 as well. Okay, we observe it only at the relatively sharp value of the parameter, which is 0.35. Then we see it. Okay, it's not super frequent, but we do see it. So intuitively now, it says that when the parameter is around 0.35, this event is possible. It's even common. But when the parameter is lower or higher, this event becomes really hard, like to imagine. So we're flipping a little bit the problem on its head, and we're saying, well, to know the value of the parameter, given that this has happened, it must not have been so rare. Right? It had to be common if it has happened. It cannot be a miracle. Of course, there's a chance that it is a miracle, but we're not going to assume that everything that happens is a miracle. We're assuming the reverse. We're assuming things happen because they can. Things happen because they are common. And so the only case in which that event was common is when the probability was 0.35. Right? So doesn't it make sense to say that the probability of association between these two alleles must be close to 0.35? It's the only case where this has happened at all in our simulations. Okay? So that's a very strange way of thinking of estimations. We're kind of flipping the problem upside down. We're not changing the observations this time. Okay? We're changing the parameters of the distribution. And we see that the only one that's remotely compatible with the observations we had is p equals 0.35. So it's not the best value ever. This is not the value of our estimate, but this is the only one that has a chance of being compatible with what we have. Right, questions about this? So that was question 16 here. So the one in which it appears the most frequently in the output is 0.35 because it's even the only one where it appears at all. And that's the reason why we believe that 0.35 is a much better estimate than 0.25, which is 1/4, or any other values that is proposed here. And that's actually a very, very deep concept, right? So deep that we're going to spend a whole week talking only about this, because it's hard to grasp really what this means. To say I'm going to change the parameters until what I have actually observed becomes possible. It sounds very weird to say it this way. So we should favor the distribution B1084P, where the observed value, 285, is as common as possible. That's what we're saying now. Other distributions should be ignored or rejected because the observations would be very unlikely to occur. So that's what we've seen. When we put it too low or too high, then 385 is just not happening anymore. This makes sense at an intuitive level, but we have screened only a few values of p. Okay, so like I've screened like 4, maybe 5. Doesn't say that 0.35 is the best ever. It could be 0.357. So question 17, the function d binom gives the probability of observing a result under a given binomial distribution. It is the numeric application of equation 1, so we don't need to know this formula, but we have a way to compute it, and that's the function d binom. That is to say, it is a deterministic function without random components. Okay, the or in or binom stands for random. The d stands for distribution. It is not a random function. It's a deterministic function. Using the documentation, if necessary, compute the probability of observing 385 with the distribution B1084 0.35. Okay, so let's do this very quickly because we have only 3 minutes and then there is a class after, so we have to evacuate relatively fast. So you will see, looking at the help page, that d binom is used very similarly to R binom. So the size is 1084. The prob is the same, 0.35. And now there is no parameter n because we don't need to produce random numbers. There's a parameter x. okay, and x is 385. So that's what I want the probability of. And so the answer is that. So this happens with the probability of 2%, 2.3%. And there is no randomness, so we don't need the set seed trick. So we're going to stop here because it's time. Like, you will have to finish, of course, the questions like 17, 18, 19, and 20. And of course, if you're interested in the extra questions, and you know what to do. If you're interested in discussing the topic of last week or this week to know more, etc., just come to the office hours and we'll talk about whatever you want to talk. So thank you very much, and good luck with the quiz for the tutorial, and see you next week.